In this work, we introduce PolyMerge, a compression algorithm for 3D Gaussian splatting models which enables provably safe navigation on platforms with restricted hardware resources. 3D-GS is a 3D reconstruction model that represents a scene as a cloud of Gaussian distributions to achieve state-of-the-art visual fidelity. This fidelity allows robots to perform multiple tasks more effectively, such as localization of objects. However, due to its large model size, it is difficult to perform safe navigation on a 3D Gaussian splatting scene without relying on powerful off-board hardware resources such as a GPU, which may not be available for many robotic systems including lightweight drones under unstable network conditions. PolyMerge enables safe navigation on board by compressing the model into a set of polytopes that can represent the obstacles in a more compact way compared to the cloud of Gaussian distributions. PolyMerge proceeds in 3 steps. First, we extract an occupancy map by dividing the scene into a uniform voxel grid and identifying all voxels that overlap with a fixed confidence interval of any Gaussian distribution. The resulting occupied voxels are shown on the right. Then, from the set of occupied voxels, we generate a set of convex hulls. While each convex hull is small and localized around a small neighborhood of voxels, the union of the hulls covers all occupied voxels. The resulting number of polytopes is typically smaller than the number of Gaussian distributions, but it is often not small enough to deploy on a drone. Therefore, we further reduce the number of polytopes in this last step, where we iteratively merge convex hulls. In each iteration, we greedily select 2 polytopes whose convex hull contains the least amount of unoccupied space, and replace them with their convex hull, which reduces the number of polytopes by 1. This process is repeated until a desired number of polytopes is reached. As shown in the figures below, we progressively reduce the hull count from 371 down to 10 at the cost of including more free space in the hulls. This allows us to load these polytopes onto a tiny drone such as a crazyfly and perform safe navigation using control pair functions. Specifically, as shown in the left figure, we can select the number of polytopes to satisfy the hardware constraints as well as the desired level of conservativeness. In addition, we modify the firmware of crazyfly to run a custom controller which generates nominal control inputs using a control app on a function, and filter them with a control pair function where the obstacles are represented with the polytopes. As a result, the drone is able to fly without colliding with objects in the experiments across 10 different start and goal point pairs, as shown in the figure on the right. Here we show videos of 2 of these trajectories, one in each column with different number of polytopes in each row. With 150 polytopes, the space inside hoops is rendered safe for the drone to navigate, which allows the drone to successfully pass through them. Meanwhile, when only 10 polytopes are used, the space inside hoops is considered occupied as a product of merging, so the drone is only able to navigate around the hoops. We also perform simulations on the MIP NERF 360 dataset, a standard dataset for 3D reconstruction that contains 5 outdoor scenes and 4 indoor scenes. This slide shows one simulated trajectory in each of the 5 outdoor scenes. Only a small subset of all the polytopes in the scene is visualized for simplicity. The indoor scenes are visualized here, with one simulated trajectory in red likewise. This is the end of our video. Thank you very much for watching.